Good morning. Um, for well-known reasons, we only have maybe 1/3 of the attendees today here. I mean, people are getting tired, and there are parties every night, and blah, blah, blah. So, Daniel, I apologize, but we have to start. And let me tell you briefly my relationship with Daniel. He started here in our lab in São Carlos when I believe you were in the first year, second year, undergrad, in the second year, and then he stayed for 15 years, more or less 15 years, masters, undergrad, masters, PhD, postdoc, etc., etc. He is now working at the ILUM. It's a new school on sciences in general, sciences. If you want to learn sciences, Daniel is one of the young professors there. And the great thing about this school is that everything is free, and the students get a salary. They get some per diems for their hotel and expenses, and they even get a laptop computer if they're approved. So this is a novel school in Brazil. Of course, it's highly selective. It's not easy to be accepted, but everything is free, and fantastic endeavor. And Daniel he became more and more interested in machine learning, computer simulations of glasses, because he has a strong background on glasses. So I believe he'll give now an overview on glass discovery using machine learning approaches. So thank you very much, Daniel, and I look forward to your talk.
Thank you very much, Edgar, for the introduction. So, good morning, everyone, and welcome to Glasses and Artificial Intelligence. My name is Daniel, and before I start, I just want to tell you that 9 years ago, I was sitting where you are. I was learning a lot during the first São Carlos School on Glass and Glass Ceramics. I am on this photo. You won't find me. I had hair back at the time. So I learned a lot 9 years from now, and 9 years before. And 9 years from now, I would love to be sitting where you are and learn something new from you. So hopefully we can do this. We can make this happen 9 years from now on the 3rd edition of this school, okay? So this is the outline of my brief talk, my brief lecture here. So let's start with a brief introduction. You all know that when we talk about glasses, we have an endless possibilities to make glass, right? We have the whole periodic table at our disposal, and we can make glass with more or less any of the chemical elements that are known radioactive, right? So this is a lot of elements. We can change the composition of these glasses continuously. So why we can do this? Why we can do this? Because glasses do not have strict stoichiometric restrictions as crystals do, right? So we can change the composition, and as we change the composition, we will change the properties. So we have this kind of control with glasses, right? We can fine-tune the glass property by changing its composition. So this is the flow chart of materials science, of materials engineer. You all know this by heart, so you have some kind of composition, some mixture of chemicals. You process this mixture, then you will have a material with a nano, a meso, a micro, a macro structure, and this material, this object, will have a set of properties, and then it's our task to find some kind of application for this material, right? This is the basic flow chart of material science. And how about glasses? Well, you know that most, not all, but most of commercial glasses, they are processed by the same route, right? This is melt and quenching. Of course, it's not all, but most of the commercial glasses, they are made by the same route. I'm talking about commodity glasses. I'm talking about very high-tech glasses. They are made by the same route. And what would you expect about the structure of these glasses? Okay, the structure will change because you will have processing variables. Perhaps you will change your melting temperature. Perhaps you will change your cooling rate. Okay, I understand. We have some processing variables, but at the end, you will have a material that kind of remembers the liquid that it was before it froze, right? So you don't have too much room to change the structure of the glass. The structure will be more or less similar because the processing is more or less similar. And because of this, the properties of glasses, they are highly dependent on the composition of the glass. Please note, I'm not saying that it's only dependent. It's highly dependent. It's quite different. This is an oversimplification, but this is something that we can exploit when we are thinking about machine learning, when we are thinking about artificial intelligence, and this is a huge opportunity if you want to work on this interface, right? Now I need to define two terms before we move forward. Inverse design and forward modeling. What is inverse design? Inverse design is when you know the properties that your material should have, and you want to find possible candidates that can meet your demands, right? This is inverse design. Where we will find inverse design? Perhaps you work in industry and you already have the project of your new gadgets that you're making. You know the hardness that the glass must have. You know the refractive index. You know the properties. Your task now is to find a glass that meets your desired, your requirements, right? And this is in red because this is important. We do not have any physical models to solve the inverse design problems. We simply do not. Physics cannot help us here. It's unfortunate, but this is the truth. If physics cannot help us here, what do we have? What can we do? We have trial and error strategies. This is what has guided glass science for many years, right? And we have optimization algorithms, right? Now I want to define forward modeling. Forward modeling is when you know the descriptor of your materials, you know how to describe it, and you have a model, and with this model, you can predict some kind of property of your material, right? This is forward modeling. And the thing is, with forward modeling, we can enable inverse design. Forward modeling can help us in the task of inverse design. And I mean, we have many strategies for forward modeling, right? We can use empirical models. We can use physical models. We can use DFT. We can use molecular dynamics. We can use Monte Carlo techniques. And we can use data-driven techniques such as machine learning. And when I say data-driven techniques, of course, the first thing we need is data, right? We need data. And we in the glass community, especially the inorganic glass community, we are somewhat blessed because we have a huge free database that is available. It's SciGlass. SciGlass is freely available. It's licensed under the open database license, so anyone can use it for research, for commercial use. So you can use it. It's freely available. It has hundreds of thousands of data points, of experimental data points, mind you. It's not simulated data points, right? And as far as I know, there's no such a thing if you go outside of the inorganic glass fields. I'm not aware if we have such rich database freely available for metallic materials, for polymers. I just don't know. I've never seen it. So this is why I say that we are somewhat blessed in this community, because we have a huge amount of data. Now, this was a brief introduction. Let's talk a little bit about forward modeling. This is just to give I already told you what is forward modeling, just to give you some example. So what is a descriptor of your material? The chemical composition, for example, is one descriptor. Perhaps the processing information is another thing that you can use to describe your material, the microstructure, and so on and so on. The descriptor of your material is the set of information that you need to somewhat describe, somewhat tell the algorithm what your material is, right? And the target is what you want your model to predict. So perhaps you have the chemical composition, and this will be ingested by some kind of model. This is the f of x here, and out it spits property, some kind of property, say hardness or Young modulus or you name it. Of course, just to remind you, the f of x is your model. It can be empirical, DFT, simulated, it can be lots of things, and we will talk a little bit about machine learning in this talk. Right? So this is a new model. I'm starting from the end, right? This is a new model published last year. It's called GlassNet. It's a deep neural network model, and it is able to predict 85 different properties of glasses and supercooled liquids by the only input is the composition. This is not a joke slide, right? So this was the input, the composition, right? This is a silicate glass. And the numbers here, they are actual outputs of the model, right? I will go deeper into the properties, into what's happening here, but this is just to motivate you on what we are going to discuss in the next slides, right? So how this model was built, right? I went to the SciGlass database, and I made a very simple query. I wanted to retrieve all the entries, all the glasses that had at least one value for these 85 properties that I was interested, right? So if the glass had at least one of these properties, I collected this information. And I did a minor chemical filtering. So I wanted all the possible glass chemistries that SciGlass have available. I wanted them to be represented in my data set, right? So the minor chemical filtering was as follows. All the glasses containing from hydrogen to bismuth, except perhaps those glasses with noble gases or promission. Those glasses, they should not be included, and this will be clear in the next slide, I promise. After this query, I end up with about 280,000 examples. We call examples in the field. Think about an Excel table, 280 lines in this Excel table. And these are duplicated entries. This is not good. If I have time, I will tell you why this is not good. So a cleaning process would be to deduplicate this data, right? I want a table with only one entry for each glass composition, right? So there are strategies to do this, and in the end, the data set had about 220,000 different, mind you, glasses in this very big Excel table, right? And of course, 10% of this data was reserved for testing. If I have time, I will dwell on what this means. Now, this is why I couldn't have glasses made with noble gases or promission, because for this neural network, I wanted to inform the model using this rich data that we have available, this rich physical, chemical, elemental information that we have, right? So if you go to any chemistry textbook, you will find lots and lots of elemental physical chemical information there. And what I want to do is to inform my neural network with this kind of data, this kind of information, right? And we have lots and lots of this information. Perhaps the most simple ones are atomic number, atomic radius, atomic volume, atomic weight. These are the simple ones, but we also have like band gap energy, boiling point, Mendeleev's number. What's Mendeleev's number? Electronegativity. We have the chemistry literature. It's so rich with all these properties of the elements, and I really wanted to inform my neural network with this kind of data, right? But as you know, it's quite hard to make glasses with just one chemical element, but all of these properties, they are elemental properties, so we need a strategy to somewhat convert elemental properties into a single value somewhat related to the glass composition that we can feed to our neural network, right? And I mean, there are many strategies to do this. I'm showing one strategy here, and the strategy is as follows. Think about your glass as a vector of composition, of atomic mole fraction composition. So vector C here, if I want to represent, say, for instance, silica glass, I would write a vector. In the first position is the atomic mole fraction of hydrogen, so 0. In the second position for lithium, 0, and so on and so on. I will only have a different value of 0 for silicon and for oxygen, because I'm talking about silica glass, right? So I will fill the atomic mole of silicon and oxygen. The other values will be 0. So I have this vector, very sparse vector, and this vector represents my glass, right? Similarly, I can also construct a vector with a certain physical-chemical property. Now let's think about the atomic number. That's quite simple. So vector S will have the atomic number of hydrogen in the same position, so it will be 1. The same position, as the composition vector, the atomic number of lithium, right? And so on and so on. So I have a composition vector, a physical-chemical property vector, and then I want to perform some calculation to, in the end, have like a single value. And I have two strategies here. One that I called weighted, and one that I called absolute. The weighted strategy is just to multiply using the Hadamard product. It's a fancy name of element-wise multiplication. I don't know why mathematicians have these fancy names, but element-wise multiplication, right? You have another vector, right? If you apply some kind of aggregator function to this vector, say a mean, you will collapse all this information into one number. You can apply like a mean, you can apply like a sum, you can apply like a standard deviation. You have a vector, you have lots of number, you can collapse this vector into a single number. You will have a weighted, a number that represents the weighted atomic number of this glass. Now you ask me, why would you do that? Why the weighted atomic number would have anything to do with predicting glass properties? I don't know. The task to understand why this is important is a task for the neural network, not for me. I just want to inform the neural network. If this is not important, the neural network will identify that this is not important, right? So right now, I just want to have more information so my model can learn patterns in the data. This is the thing that I want to do, right? The other strategy is what I call the absolute feature of the glass. Before multiplying the composition and the physical-chemical property vector, we apply a CEOL function to the composition vector. What the CEOL function does, it converts any number to the closest integer that is above it. So all the 0 values will still be 0, but if you have any non-zero value, it will be 1. So this A value, it is only sensible to the presence or not of the chemical elements. Again, why am I doing this? Because I want the neural network to have two kinds of information. A weighted information, so it can fine-tune its prediction, and an absolute information, so it can somewhat group the different glass families. The different glass families may be grouped by the chemical elements that they are made. So I wanted something that did not vary with the amount of the chemicals that we have in the glass. Okay. In the end, if we do this with all the physical-chemical properties, with all the aggregator functions, with the weighted and absolute features, we will end up with more than 600 features. Think about an Excel file with more than 600 columns just to describe your glass. And this is far too much. This is far too much. We can do better. We can select only those features that are more relevant to this problem. And I mean, there are many strategies to select the features. For this work, what we used was the variance inflation factor. This is a strategy to remove the multicollinearity of the data. What is multicollinearity? If you have one feature and you can easily predict this feature by a linear composition of the other features, then this feature has a high multicollinearity regarding all of the features. So in the end, if you have a high multicollinearity, this feature is not bringing a lot of information to the table, because all of the others together in a linear fashion, in a linear combination, will have the same information that this one have. So we can remove features considering this kind of computation. And in the end, we have close to 100 features. This is much more manageable to train a neural network. So we will go from here. Just to give you an overview, I talked a lot, but just to give you an overview, this is what we have. We have a model that receives the chemical composition. The chemical composition goes into a feature extraction process where we retrieve these 98 physical-chemical features. These features, they are fed into a neural network, and this neural network spits out 85 different properties. This is what we call a multitask learning. If the neural network predicted just one property, it would be a single task. But by predicting more than one, it's a multitask. Simple as that. And just as a note, many of the previous works in the field, they were focused on oxide glasses because we have much more data on oxide glasses. But just as a note, this was not the case here. This was not a limitation of this model. We trained it with all the chemistries available inside glass to see what happens. Now comes the hard part. The hard part is, what is a reasonable neural network architecture to model this problem? And this is the hard part because for each different problem, we will have a different neural network architecture that best models this problem. So this is not good. And on top of this, discovering the best neural network architecture that models your problem is an NP-hard problem. What this means is that to discover the best architecture, you need to test them all. And we have infinite architectures possible, that are possible. So we cannot have the best architecture. This is unfortunate, but we cannot have the best architecture. The best we can do is to find a reasonable neural network architecture that can model our problem. And this is a very involving task because we need to intelligently test many architectures, and we need to select the search space of the architectures. It's hard stuff. I just want to show you that this was done in this work, following lots and lots of procedures. This is not the focus of this talk, but if you want to discuss this, we can drink some coffee and discuss this. And after doing all of these steps, we finally find a reasonable neural network architecture, and we can finally train the final model, and we can finally have a neural network that can predict 85 different properties of glass, that can predict these properties reasonably. It's not perfect. I tell my students, if you want perfection, run away from machine learning. Machine learning is not perfection. Machine learning is trying to predict something reasonable, right? So this is what we can do. The performance is reasonable. It's all written in the paper. You can check that. And we can predict 85 properties by only have the composition. This is the main idea. It's quite hard to see all the properties here. That's why I just grouped the properties so we can predict viscosity, we can predict optical, electrical, dielectrical, mechanical, thermal, and so on. We can predict lots of properties with this neural network. Now, one question perhaps might be, why multitask learning? Why don't you just simply train like a single task neural network or a single task machine learning algorithm for each of these properties and be happy? You don't need a multitask learning. Now, this is the justification from an idealized point of view. This is just something that to show you the idea. When I show you this picture and I ask you, what is this? I bet that most of you will tell me, well, of course, this is a kangaroo. This is a kangaroo, right? Okay, great. Now, if I ask you where this photo was taken, you will tell me, I don't know. But I know that kangaroos, they are native species from Australia. So my best bet is that this photo was taken in Australia. Perhaps it was taken in a national park, in a zoo, anywhere else. But my guess would be Australia. Then I ask you, what language people speak where this photo was taken? Well, Australia, people speak English there, it's English. What's the accent of the people, of the English spoke where this picture was taken? Oh, it's the Australian accent. They say like, hey, mate, or something like that. What's the food they like? Oh, Australians like barbecue. Look what you've done right now. I just showed you a picture of a kangaroo, and this was really easy for you to answer these questions because your brain connected the information without you needing to think hard. Your brain connected information because you know about geopolitics and biology and stuff like that. You know that. And you could answer these very hard questions without blinking an eye. And the idea is to exploit this kind of multitask learning with this neural network. So perhaps my neural network, while it's learning how to predict the glass transition temperature, the hope is that perhaps this can help it predict viscosity. We know that they are related somehow. Perhaps in a dream it can help me predict Young modulus. I don't know. Let the neural network do its best to try to connect this information because in the end it's just one model. This model will need to be able to predict 85 properties and try to connect the information of all these data points and spit out 85 properties. So perhaps in the end, the neural network can do what we are doing with this picture. And this was the motivation of this multitasking model. And the final question. Was this beneficial? Yes and no. It's kind of bittersweet, but this is what it is. Science is like that. Well, we cannot force the result. Multitask learning was better than single task learning for this specific model for glass properties that are measured in different conditions. Let's think about viscosity. When you measure viscosity, you measure it at different temperatures, right? Viscosity change with temperature. So it's the same property, but measured at different temperatures. For these cases, multitask learning was awesome. Now, for some properties, multitask learning and single task learning, they were statistically equal. Okay, it's life. But for some properties, a single task, a specialized model was better, right? Which properties? Properties that we had lots of data points and properties that were not measured at different conditions. For these cases, it was better to train a single task neural network. And this is life. But we have a solution. We can build a hybrid model. Nobody will stop us. So we can predict the best properties with the multitask learning and use the single task learning, the specialized model for those properties that the single task model performs better, okay? So this is actually, GlassNet is a hybrid model. And a neural network, perhaps you've heard this, a neural network is a black box model. We have lots of weights, lots of bias, lots of numbers, lots of computations, but if you try to look into what the neural network is doing, you cannot just tell, oh, it predicted a value of 1,000 Kelvin for TG because it found this, it found that. You cannot do that. It's not interpretable, right? But we do have some tools that we can use to somewhat understand patterns inside the models. And SHAP is one of these tools. So this is an algorithm that goes through your network looking for patterns, and it spits out some interesting information. This is correlation, this is not causation, mind you, this is statistics, this is the lecture 0 of statistics. I'm not saying that there is a causal relation, but we have a correlation, and this is something that we can try to exploit when we are designing our glasses. So just to show you that this is possible, we have a plot for young modulus and a plot for the temperature where the crystal growth velocity is maximum. So if you're interested in glass ceramics, this is the temperature that you are interested in, right? Perhaps you want to increase your temperature of crystallization. Then you should decrease the amount of sodium. You should decrease the amount of boron. You should decrease the amount of lithium. You can increase the amount of aluminum, right? This is the kind of information that we can extract this causal relation between your inputs and your outputs. And then when you are messing around with the composition, trying to find the glass that you want, perhaps this can guide you instead of going blindly. Perhaps, oh, I know, this has a huge impact, this has no impact at all. At least empirically, right? This is an iterative process to find the glass that you want, right? And this is just a collection of information by property groups. So if you're interested in changing viscosity, what are the chemical elements, what are the features that have the most impact on viscosity? So boron, sodium, aluminum, potassium. No, I'm interested in optical properties. Of course, lead, bismuth, titanium, niobium, right? So I'm just saying, if you are designing your glass, perhaps having this table right beside you can be helpful so you can fine-tune your glass composition. Perhaps you will find your glass with less interactions, right? Now, by having GlassNet, we can also build on top of GlassNet. And I'm showing you some experimental data points for that, for viscosity, for that glass composition over there. No, I'm just kidding. These are not experimental data points. These are data points predicted by GlassNet, right? These are predicted data points. They have a very nice consistency, and we can just fit our favorite viscosity equation. We have the VFT, Mayega, Avramov-Milchev. We have lots of viscosity equations. We can predict the viscosity with GlassNet and fit with our favorite equation. So now we have a model, a interpretable model that we can then use, I don't know, to design our glasses, to melt our glasses. I don't know. Viscosity is really important, right? We can do this for silicate. We can do this for chalcogenites. It's much more fuzzy, the data points, because we have less data points for chalcogenites, but still, we can fit a model and see what happens. I mean, I will repeat, if you want perfection, run away from machine learning. Machine learning is not perfection. But now, if I asked you, what is the viscosity of this complicated chalcogenite? I don't have a better guess than this. So at least we have a starting point. This is my main point here. And this is a little bit of marketing. I'm developing this free and open source Python code. So if you know Python, and if you're interested in using GlassNet, GlassNet is freely available there. I mean, it's there, you just download and use it. GlassPy also has the SciGlass database in a very nice pandas data frame. For those who know Python, this is like the Excel for Python. Very easy to use, and it's free, it's open source. So I invite you to check out if you are interested. Now let's talk about physics-informed modeling. We do not need to throw away the physics that we know if we want to use machine learning. This is not necessary. We can inform the models with physics. And here I have a pipeline of another model. It's called ViscNet. It's more or less similar to GlassNet. We have a input stage, we have a featureization stage, we have the neural network, and we have an output. But the difference here is that, let me see if I can use this. The neural network, it predicts the parameters of viscosity, right? And the prediction of viscosity is done by a model. In this case, it was the MAIGA model, but you can change the model. The model is not the important part here. The interesting part is that the actual prediction is done by a physical model, or empirical model, if you want. And when you are training this neural network, the training process, the backpropagation, the changes of the weights and biases, it goes through the physical model. So the parameters of the neural network, it cannot go wild. It must follow what the model is telling it to do, right? And what's the advantage of this? Here we have a liquid that was not used to train ViscNet. So this is a new liquid. We have the prediction bands of ViscNet, and now you tell me, oh, I want to extrapolate my prediction, right? Because I'm interested in, I don't know, relaxation below TG, or I'm interested in really ultra high temperature viscosity. I don't know. You want to extrapolate. When you have a neural network, it's quite difficult to extrapolate. Perhaps you've heard about this. Neural networks are very good interpolators, but not extrapolators. But in this case, who is extrapolating? It's the physical model. So this is one of the advantages of informing our machine learning pipeline with physics, because physics will constrain the prediction into something that makes sense. So we do not need to throw away physics if you want to do machine learning. This is just another example. It's a recent paper where we studied hardness of glasses, trying to predict hardness with machine learning. And when we inform the model with an empirical model, a physical model, the low dependence of hardness is reasonable. And when we do not do this, the neural network goes crazy. It's the blue triangles is without physics, and the green points is with physics. Again, I'm telling you, if you want perfection, go away from machine learning. This is not perfection, but we are capturing the essence of hardness, that of the low dependence on hardness here. This is the idea, right? Now let's talk about inverse design. Just to remind you, inverse design is when you know the properties that you want, and you want to find some suitable candidates that meet your design. And this can be enabled by forward modeling. Just to remind you, we cannot solve this problem with physics. If you know how to solve this with physics, let's have a drink. I would love to know, but as far as I know, we can't. So we need to use other solutions. For many years, we used trial and error, and I mean, this helped us until now, but we can do better, right? We have optimization algorithms that can help us navigate the search space of glass properties. But to use optimization algorithms, we need predictive models, and this is why we need forward modeling. Perhaps you already know some optimization algorithms such as grid search and random search. They are very well known. However, think about the search space. We have an infinite search space because we can control the glass composition continuously, remember? So it's quite hard to find what you want with random search, especially if it's a difficult problem. If your design constraint is quite difficult, random search will take a lot of time to find a solution for you. And grid search will not converge if you have a very huge search space. So we need somewhat another strategy. And what I will suggest to you today is genetic algorithms. They are an optimization algorithm. They are optimization algorithms based on Darwin's evolution theory. I will not get into the details. Again, if you're interested, we can drink some coffee and we can discuss the details. This is not a lecture on genetic algorithms. I just want to tell you that this is a very powerful algorithm where you can solve single and multi-objective problems. Multi-objective problems would be, oh, I want to increase hardness and decrease young modulus, and I want to increase refractive index, and so on. You have more than one design constraint in your problem. You have fully control on the search space. So perhaps you want to avoid some kind of chemical element, because it's toxic, or perhaps you want to avoid some chemical components you want to search only in certain ranges for these compounds, right? And you can apply constraints, right? Try to find the glass that I want while minimizing the cost, while avoiding some patented compositions. So we have a lot of control in our genetic algorithms. It's a very powerful algorithm, and this is my suggestion for you. And I will show you success work that we did using this kind of strategy. So we wanted to find new glasses to apply in smartphone lenses. Smartphone lenses, glasses, they are made by precision molding, and you cannot have a glass with a TG higher than 500 Celsius because it will damage the mold, right? You do not want to damage the mold, otherwise they are very expensive molds. So you need to keep your TG restrained below 500 degrees C, right? And of course, you want refractive index that's high because we are talking about optical lenses. To solve this problem, we used neural networks to model refractive index, to model the glass transition temperature. This was before GlassNet, so it's the grandfather of GlassNet. And we use genetic algorithms to guide the search for these glasses. And long story short, we had lots of candidates. From this list of candidates, we selected 2 glasses, and as you can see, they are multi-component glasses. They are glasses that I think would be really difficult to design just by trial and error due to their complexity, right? I'm not saying that it's impossible, but you agree, right? It's quite difficult to get to these compositions just by thinking. But if you know the interaction of boron with lithium, with calcium, with antimony, it's quite difficult. But this whole process, this whole pipeline was able to somewhat find these connections. And let's see what the neural network predicted for us. Okay, seems reasonable. We do have glasses with TG below 500 C and refractive index above 1.7. This is at least these are the predicted values. Then we made the glass, and we got it. Now remember, it's not perfect. You're probably looking, oh, you missed TG by a lot on the second glass. Yeah, that's not good. But I understand, I fully understand. It's not perfect. I understand that's not perfect. But you see, we are not hiding anything here. We could have done, melted 10 glasses and only showed you 2 glasses. But we really only melted 2 glasses. And this is a work with Professor Zanotto. You know Professor Zanotto. We are not experts in optical glasses, right? Professor Zanotto is an expert in crystallization, many things, but we are not working with optical properties, at least not when I was in Professor Zanotto's lab. But we were able to go outside our comfort zone and find 2 new glasses that meet a very strict design constraint, right? Another thing, these are really different. These are sufficiently different from the glasses used to train the neural network. Because people can say, oh, this is a similar glass. The neural network is just parroting what it knew. No, it's not. These are quite different, and they were not published yet. So these are original, right? So this is somewhat powerful, I think. Now, for some closing words, as I told you, infinitely many glasses can be made, and these artificial intelligence / machine learning strategies can help us solve this problem. And as I'm talking to a young audience, I want to invite you to build an open science environment. So if you're interested in machine learning, in data science, in artificial intelligence, and you are building these tools, I invite you to open your science, to help the community, to build this healthy environment so we can all thrive together, right? This is my invitation to you. And before I show you I don't know if it's the last slide, I want to thank my collaborators, in special Professor Zanotto, you know Professor Zanotto from the Federal University, Professor André de Carvalho here from the State University, from the Computation and Statistical Department, and the international collaborators. I understand that Colin sent some oh, great, nice to meet you. So John Mauro, Colin Wilson, Anup, Krishnan, and Sarah Lek, our international collaborators. Now, this is the end of part 1. I need to ask the chair, how much time do I have? I need like 20, 25 minutes. But I can go faster if you want. I will keep to 20 maximum. Okay? Okay, so this is the end of part 1. Now I will start part 2. And this is a question that always comes when I give this kind of talk. How to start using this kind of tools? Okay, I'm a glass scientist, I'm a material scientist, and I want to start using this kind of tools. So these are some tips if you want to start. This is very basic, so if you already know machine learning, you already know data science, you will, probably you can get some coffee. It's really basic, right? First thing first, nobody does machine learning by hand, right? You will need a programming language. And you can use the programming language that you know. I mean, you know C, you can use C. You know Java, you can use Java. You can use the programming language that you know. If perhaps you want to know a new programming language, or if you already know Python, then that's great. Python is right now, if I may say this, is the language of science, so it doesn't hurt to know Python right now. It's quite easy to learn, it's quite readable, it's free and open source, and it has the state-of-the-art machine learning models, so yeah, I think it's a good start. If you want to use Python, before machine learning, I will recommend you to install a few modules because it will be easier if you have these modules. You will need NumPy because everyone needs linear algebra, because machine learning is like a glorified linear algebra. Everyone knows that. So you will need NumPy. It has all the linear algebra that you want. It's fast. Go for it. I have some links where you can learn more about these modules. I can send you the slides. I can send you the slides if you want. You don't need to write this down. You can take photos. I don't mind. I have some links. Feel free to use them to learn. You will need SciPy. If you're doing science, you will need SciPy because SciPy has all the things about optimization, integration, interpolation, differential equations, a statistical toolbox, and much more. So if you're doing science, you will want SciPy because yes, yeah. we all need at least a good statistics toolbox. If we are working with data, we will need pandas. Pandas is like the Excel for Python. Remember when I told you that that GlassPy had a SciGlass in the pandas data frame? This is pandas. It's very, very powerful. It can do lots and lots of data analysis and data manipulation, so you will want pandas. And you will want Seaborn because you will want some very good module to plot your data, to have very expressive plots for your papers. I'm just showing a few examples here. They are quite beautiful, they are easy to use, they are focused on science, right? Of course, we have many options. We do have many options. If you want one suggestion, I would suggest Seaborn. Now, let's talk about machine learning. I'm going fast because this is a 25-minute talk, right? What machine learning can do for you? First, I need to ask you what you have. If you have the descriptors of your material, the descriptors of your glass, and you want to predict something, then machine learning can help you, and the field of machine learning that you are interested in is supervised learning. Supervised learning is the field that connects descriptor with targets, inducing a predictive model, right? It comes into two flavors. We have regression, when your target is continuous, and we have classification, when your target are labels. Depending on our problem, you will have to select one of these two flavors. If you have the descriptors of your material, but you don't have anything to predict, at least not right now, you still can use machine learning. You want to check unsupervised learning. Perhaps you have lots of micrographs of your metallic alloys, of your glass, of your crystals in glass, and you just want to group these photos into clusters, right? Perhaps by the crystal shape, the crystal structure, I don't know. You want to group them. You have a clustering problem. You don't want to predict something. You just want to group them. Perhaps you have lots of signals from NMR or Raman, and you want to decompose your noise, sorry. You can use unsupervised learning and outlier detection, and so on and so on. This is not an extensive list, right? I'm just showing you the main ideas. And machine learning needs data, of course. You can bring your own data. You can collect from the literature, right? You can go to handbooks, you can go to papers, you can collect. You can use databases, you can use data set aggregators. We have the materials project with lots and lots of simulated data. We have the Open Quantum Materials database, the A-Flow database, the Nomad project. So we have lots and lots of data. If you just want to learn, I just want to learn, you don't need materials. You don't need a materials data set. Go to Kaggle. Kaggle has lots and lots of data sets, lots and lots of different problems, regression, classification, clusterization. Go to Kaggle, and it's a very good starting point. You don't need to start with materials data set, right? And of course, if you want glass data, please go check GlassPy. Now, this is the part that, as a reviewer, most people get it wrong. This is why I will take some time with this slide. Say you chose to do machine learning. Okay, I will do machine learning. You need to think ahead. What is your final objective? If your final objective is to have a predictive model and be able to measure, to check the performance of this model, and I mean, who wouldn't want that, right? You need to check the performance of your model. If you don't know the performance of your model, you are in a dark room without a candle, right? So if you want to check the performance of this model, you need to think ahead. Stop. You need to get your data, split this data into what we will call a training and a test data set. And the test data set, you need to hide it away, lock in a closet, and never open it again until the very end. I cannot stress this enough. If you look into this data before the very last step, you are doing it wrong. And this is not good. This is where people get it wrong a lot of times, believe me. It's just as simple as this. Lock it away, never look back, and do everything you want with the trained data set. I mean, everything you want. But this, you do not touch. And now we have another very important thing that may cause some errors. Data leakage. You simply cannot have information from your test data set to leak into your training data set. You can't. This is forbidden. If you do this, you will think your model have a good performance when it does not. This is not good. And the worst thing, I mean, you can think that a worst model is the worst thing that you can have, but this is not. A worst model that you think is great is the worst thing you can have, right? You cannot have this data leakage. If your data has duplicate entries, when you are selecting randomly the data to build your testing data set, you have a chance that is different than 0 to select one class and keep a duplicate in your testing data set. So if you have a duplicate data set, you have a chance to do this, and you have information from your test data set that leaked into your trained data set. This is not good. Please do your research. Don't let data leakage mess with your model. Okay? Now, we do have a very nice paper by Sebastian Rashka, about 50 pages. It's free, available on archive. 50 pages. This is the only thing I'm asking you if you want to start in this field. Please read this paper. It's the only thing I'm asking. In this paper, he goes through all the details, what you can and what you cannot do, in a very simple and clear, with pictures, fashion. Please read this paper. This is very important. Now, we have Python. We have all the bases. We know what we want to do. We can use machine learning. Python has this very nice module to do machine learning called scikit-learn. It can do supervised learning, unsupervised learning. It can do data set transformations, and so on, and splitting, so on, so on, so on. Very complete. Go check it out. Very good user guide, very good user guide. Go read it out. And what I want to do with you right now is to train our first model. I want to train a linear regression using scikit-learn. Linear regression, it rebranded itself. It's now part of machine learning, right? So we knew linear regression from statistics. Linear regression, nobody likes it. But now it rebranded itself. Now it's part of machine learning. Now it's fancy again. I want to train a linear regression with you using scikit-learn. And I will show you that the training part is really easy. Suppose that you already have your X, your descriptor, and your Y, your target. So I'm not showing this code today. You already have code where you built your X and Y variables. This is what you need to do to train your linear regression. 4 lines of code. You import your model, you instantiate your model, you train your model, and then you can use the model to predict whatever you want. 4 lines of code, and you have a linear regression. And you tell me, linear regression, everybody can do linear regression. I can do it in 2 lines of code. Okay, now we want to train another different machine learning algorithm, random forest. I will not get into the detail, but it's much, much more complicated than linear regression. It is an ensemble full of decision trees, made with baggings method. There's a lot of involved things with pruning, with and so on and so on. This is a very complicated model, very, very powerful, but very complicated. Let's train a random forest. 4 lines of code. We import the model, we instantiate the model, we fit the model, we use the model to do prediction. I like to say that you, as material scientists and engineers or chemists or physicists, you know the hardest part. You know the hard part. That is material science, chemistry, physics. Doing machine learning, of course, you need to do your homework, you need to read the references. But in terms of code, I mean, it's not that difficult. It's not that difficult. Try it for yourself. Now, In the interest of time, I will not tell you the difference between a linear model and a random forest, but believe me, they are different models, each for different things that you want to model. So go ahead, just check them out. I don't want to take more than 20 minutes. Talking about neural networks was the topic of the first part. You probably know neural networks from these famous models. You probably heard about AlphaFold, AlphaGo, ChatGPT, Dolly. These are all neural network powered models. So these are very powerful models. If anyone here uses ChatGPT, it's really fascinating, right? And neural networks are one of the most powerful machine learning algorithms that we know. For regression problems, we can have like a universal regressor. If you have a continuous data, there is a neural network that can model your data. This is proved, right? I don't know the architecture, but there is. Out there, there is one architecture at least that can model your data. And for Python, we have PyTorch. PyTorch is a state-of-the-art free module for Python. It's not that easy to use, but I mean it's not that hard too, so there is a balance there. It's free, it's open source. This is my recommendation if you want a place to start. And if you ever want to use neural networks in your work, please watch this lecture by Andrea Carpati. 2 hours, I know, it's not short, but please watch this lecture. Andrea Carpati builds a neural network in this video from zero till the last part and training this neural network, telling you clearly each and every step of a neural network. If you are going to use a neural network, please use it with confidence. And if you only have 2 hours to learn this, please watch this video. Oh, sorry. Sorry. This video, not... okay. This video, Andrea Carpati, very good. Now, if you want to understand the main ideas of machine learning, I mean, it's a totally different field from material science, right? So lots and lots of things. If you want to understand the main ideas, not the mathematics, not the statistics, the main ideas, go check this channel by Josh Starmer. It's called StatQuest. It's quite silly. It's quite silly. I admit it's quite silly. But if you can go past through the silliness, you will find a very rich, detailed, and clearly explained lectures on what the models do, what the processes do, and this will give you confidence to use this kind of tools. And I mean, if you want maths and statistics, I have 3 books here. The first 2 books, they are more hands-on. I myself am a hands-on learner, so I like to learn and code and see what happens and mess around and change things. So these 2 first books, Machine Learning with Python and Scikit-learn, and Hands-on Machine Learning with Scikit-learn, Keras, and TensorFlow, these are very good for hands-on learners. But if you want to go deep, the last book has lots of maths, lots of statistics, and you can really learn what's the theory behind all of these algorithms, right? And the last one is free. You can search online, you can download the PDF for free. And this is what I had to say to you right now, so thank you very much for your attention.
Daniel? Oops. Obrigado. Thank you. Well, we have some minutes for questions. Today, at exactly 10 a.m., we will have an online talk, one of the few online talks. This is the research director of CCJAM, which is one of the most important glass companies in the world. So we have, please be back here before 10, a little bit before 10. So we have maybe 10 minutes or so for Q&A, and then a nice coffee break.
Awesome.
And let me start, Daniel, asking you, you have a slide with the most important features for certain properties. Mm-hmm. So let's review that slide a little bit, please.
Yep.
Yeah, okay. So, most important features for glass design. Let's take viscosity. You're saying that boron, sodium, aluminum, and other ions, and then I'm not sure what's NFS. What's NFS?
Number of field s orbitals.
Number of
Field s orbitals.
s orbitals.
S orbitals,
Okay.
yeah.
And delta HM is the melting
Melting enthalpy.
enthalpy of what?
Oh, the
This
elements.
linear
The elements.
combination. No. Of which element? Of the
The
linear.
elements of the glass. Yeah, yeah.
The linear combination. This
Yeah,
is
yeah,
a
yeah,
linear
yeah.
combination of all the elements of
Yeah,
the glass.
following
Okay.
this strategy
Okay, the
here.
linear
Yeah.
combination. So go back that, please. Okay, yeah. So what you mean by most important features? I mean,
Oh, yeah.
why silicon is not
Yeah,
there? You
yeah.
know, why zirconium is not there?
Yeah.
You know,
It's in this important is relative, right? In this case, these are the most impactful features when we think about how much they change these properties for up or for down, right? Increasing or decreasing.
yeah.
So by changing, what I'm saying is, what the SHAP analysis is saying is that changing the amount of boron will have the highest impact on viscosity, for better or for worse, than changing calcium, for instance, that's below in this list.
Right. Right. Well, that's a long discussion anyway. but
Okay,
I
okay.
could ask you, you know, why not tungsten is on the list of optical properties, for instance. Tungsten.
Why is it not?
Yeah, tungsten
Yeah,
has
yeah.
a huge effect
Sure.
on refractive index, for instance.
We cannot, we always need to remember that we cannot do better than what the neural network learned.
Right.
So perhaps for this, in this case, it could not extract this kind of information. I don't know why.
Or not enough
I don't know
training.
why. Not enough training.
Not enough
Remember,
compositions with
I found
tungsten.
I found a reasonable architecture. If it was the best architecture, perhaps this would be more evident. Right. But the best is impossible. The best is impossible.
Okay, thank you, thank you.
Thank you.
Questions? Please identify yourselves because you are live on YouTube.
Hi, I'm Henrik Brattmüller. I'm a postdoc in Edgar's lab. Thanks, Daniel, for this wonderful talk.
Thank you.
I have one suggestion or a question. There's one point where you could be a little bit more transparent, and that's when you were discussing single task versus multitask algorithms. And I wonder, could you go back to the slide where you showed in how many properties the multitask model was better than?
This one?
I wondered, are you hiding something here? Maybe
Why?
the better results in these 24 properties are all viscosity properties, you know, the viscosity.
No,
that-
no.
And all of the worst results are all of the other things.
No, this was just an example.
So to not put it differently, you probably don't have this in mind, but that's, you remember in what properties it was better or worse?
Well,
No, okay,
not
that's
by
fine.
heart, but viscosity was on one of these properties. Resistivity, density, and thermal expansion coefficient, if I'm not mistaken, are examples of properties within this 24 property group that I showed you. Yeah, but not all of them. This was something that it was clearly stated in the paper. It was not that clear, right? It was not. It was something that it is something that we are working right now to try to check if we can somewhat find a more reasonable pattern here. This was not that clear, but it is stated in the paper. I'm not hiding anything. This is just for the talk.
Sure, thanks. And a very quick follow-up question. You said it's already difficult to train the multitask models. It's challenging.
No, for all models. For all models, this is
But then
difficult.
isn't the hybrid model like exponentially worse to train?
No, the hybrid is just collecting different models into a box, right? So you train your multitask, you train each of your single tasks. For each of those, you have this pipeline. And then only for those properties where the single task performed better, then you have your box, right? You have all your predictions. For those who predict better, you use the single task prediction. You just use the number that you want because the model is yours.
Okay, but for every single task problem you will have to find a different, unique, what's called?
Architecture of the network.
Architecture.
Yes, you have.
So, if it took a very long time for the hybrid model, it takes that time plus for, okay.
Yep.
So
Yeah, but this,
takes
just to
much
be clear, this was not done in this paper. The architecture was the same because this was something that during the review process was discussed. The architecture should be the same so we have an even field. So this was not, this was in the review process. I cannot control the review process.
For sure. Thanks for the discussion.
Questions?
Hi, Jacob, UC Davis. Very interesting and informative talk. I liked all the examples and references that you provided. I can wrap my head around comparing 1 mole percent of boron to 1 mole percent of phosphorus and how that can be a very easy comparison in terms of how much of an impact it has on some property. Mm-hmm. But how do you compare that to, I think you had N sub Fs or delta H or something. How do you compare things that are in different dimensions or something? I guess or different units entirely.
I see. You are probably talking about this, right? Or this?
Yes, this one.
Okay. The thing is, of course, if you want to change your glass composition, thinking about the enthalpy of melting, the weighted enthalpy of melting of the chemical elements, this is difficult. I totally understand, because it's a much more involved task. But stop thinking about you and thinking about the neural network, because this is what's happening here. The neural network received an Excel table with lots of data points, some with higher enthalpy of melting, some with lower after the calculation. And then for this algorithm, for the sharp analysis, it just checked, for those that have higher, if you change this in this table, we are only thinking about changing the value, not the actual value, right? Changing, if you increase or decrease the value. It's just looking into, if you increase this, the impact on viscosity is that. If you decrease the impact, you're checking the impact. But I totally agree that if you're thinking about designing your glass, it's much more difficult if you're thinking about enthalpy of melting. Perhaps we need to translate this back into compositional dependence. But this is easy because we have all the numbers.
Okay, cool. I'm glad you said that because I was going to say, I don't think about making glasses in terms of the enthalpy. I think about it in terms of the composition.
Yeah, but we can go back. We can go because this is a linear strategy, right? This is a linear combination. Cool. We can go back from one to other. Yeah.
Of course. Awesome. Thank you very much.
Thank you for this amazing Ecem Bakırmak from Alfred University. Could you open the most important feature slides? Thank you. When we look at this slide, where is the thermal properties? It is not most important. For example,
It's not here, but it's in the paper.
Okay.
Yeah.
Okay,
Sorry about
I
that.
Understand. Thermal conductivity, heat capacity, you also calculated, or it's very important features?
Yeah,
because I only saw enthalpy in here, delta Hm melting.
We have the. Sorry, I don't understand the question.
You also include thermal properties?
Yeah, we do have thermal properties. Okay. We have the heat capacity,
Thermal
expansion coefficient, liquidus temperature is a thermal property, I guess.
Yes.
Yeah.
Okay. Thank you. Other question about linear regression, and you mentioned random forest model. So when we think about these two models, you have any kind of study compare the accuracy of the models? Because you compared the models' properties in your last slides, but where is the accuracy of when we think about, for example, any kind of study? Which model accurate than the other?
I see. You mean the performance of the model for each of the properties,
Yes.
right? This is clearly stated in the paper. We measure the root mean squared error. So you have an uncertainty that has the same unity of the property, right? So if it's TG, these errors in Kelvin. This is all reported in the paper. For some properties, it was close to the literature. For some, it was better. For some, it was not. For example, resistivity. Resistivity is not easy to predict. It was not that great. It's all reported then. Yeah.
Thank you.
Hi, thank you for the talk. It was wonderful. I'm Anthony from Lehigh University, and I was curious, when you were showing the two glass compositions that you created from the model, does it take into account how easily the composition is able to form a glass?
Nope. This was human intelligence. This was not artificial intelligence.
Okay, would there be
And
any
you
way-
are right in front of the human being that did this process, Professor Zanotto.
Would there be any way to try to predict how well it forms a glass, or?
Glass formation ability, it's quite difficult to predict. We've just submitted a paper where we used the glass net to try to predict glass forming ability, and it's not great. It's at best it's reasonable, because glass forming ability it's a mess. Nobody knows the exact way to predict this. This is still a condensed matter mystery, if I may. It's not good. It's not good. This is a challenge, and at least for this kind of experiment, you can inform your genetic algorithm. Say, for instance, do not search for those glasses with less than like 50% of glass formers. You know, you can add constraints as you want. You can add this kind of constraint, and this will help you to find liquids that are reasonable glass formers, but this will not be a guarantee, of course.
And just a quick follow-up. If you had the data of compositions where it was stated that these do not form a glass, would that be beneficial to the predictive model?
If you had what, sorry?
If you had data that stated this did not form a glass, would it then be able to more easily predict?
I'm sorry. If you had what? I'm still not.
If you had data where the composition was stated to not form a glass.
Oh, I see. You want to train a new model, and you have the label forms glass and do not form glass. Is this what
Yes,
you're
yes.
saying? Yeah. Then you are talking about a classification problem. We try to do this. Me, Professor Zanotto, and our Indian collaborators, Anoop, we tried to do this, and it was not that great at the time. It's glass forming. I mean, if you want a challenge, guys, glass forming, predicting glass forming is the challenge right now. This is a very good question, but it is the challenge right now.
Yeah, if I could add a little bit, because we have been dwelling on this problem for some time, and this young guy here is actually working exactly on this problem. The prediction of glass forming ability, as Daniel said, is very difficult. And I think one of the best models so far is the Jessica model, where you have the viscosity at liquidus. You know that a high viscosity at liquidus is good for glass forming ability, but you need a thermodynamic parameter too. And this thermodynamic parameter is the liquidus itself. So if you divide the viscosity at liquidus by the liquidus itself to the square power, I think that's a very good predictive parameter for glass forming ability. However, when you do all the training for viscosity, it's good, but not good enough. There are errors that big. And then there are errors in the liquidus. When you divide, one by the other, you propagate the errors. So in the end, it's a huge uncertainty. That's the problem, right, Daniel?
Yeah.
You come up with a huge uncertainty. If we could predict precisely the viscosity in the liquidus, then we'll be in good shape, I think. So we have to find for alternative things, like, maybe some of these chemical parameters could help us, but still, I mean, a linear combination of the chemical parameters is also not a very good model for the thing. Anyway, I agree with Daniel. This is an open problem. Very important open problem.
Very important.
And that's the task of Rafael here to solve, right? Or other people. Anyway, let me check the time. 9:30. Maybe one final question to Daniel. Jacob again.
Hi, me again. I was wondering, is there work being done using these types of models to figure out the more fundamental aspects physically that lead to these changes in properties? Because, I mean, not to just dwell on the same question I did before, but boron itself isn't the fundamental physical thing that changes a glass. There's deeper levels to it. Is that something that people are doing, or is it mostly focused on this composition or, I guess, bulk properties?
Yeah. I guess people are doing this. I saw this talk by Adama Tandia from Corning, and he was doing this strategy called symbolic regression. Symbolic regression is using all this machine learning strategy to obtain a mathematical expression to model your problem, right? So think about Kepler. Kepler took Tycho Brahe's data and developed the empirical equations, right? This process can be done with machine learning. If you have the data and you inform the model, you can multiply, you can add, you can exponentiate, you add your operators. The model can try to find like a mathematical expression. Then the physics is the next step. Then you will need, we cannot automate Newton yet. We stop at Kepler right now, but you will need to be your Newton for your data set, right? Symbolic regression, people are doing this, but I don't know if there are any recent papers on this. Are you familiar, Edgar? I'm not familiar. Recent papers. Yeah. We try, yeah. I tried with GFA, with glass stability. I tried with dissolution. It's not easy. The thing is, it's not easy. It's not good for too many features. You need to have 5 at most. So you need to be very selective. What will be the input of your equation? This is not easy. This is not easy. The convergence is not fast. But I mean, the tool is there. If you have a data set, this is the search time for you, symbolic regression.
Awesome, thank you.
No problem.
Daniel, maybe a final comment that your talk was fantastic, but I believe you did not stress enough that glasses are wonderful materials for machine learning.
For sure.
Because of the lack of microstructure.
Yeah.
That's why most properties are composition dependent.
Yeah.
If you go for crystalline materials, then of course it's composition. All properties are composition dependent, but they are also microstructure dependent. Then you need much more information, the grain size, the volume fraction transform, the shape of crystals, blah, blah, blah. the task is much, much more difficult. With glasses, in principle, for many properties, not for all of them, you know, it's all embedded in the composition. So it's our task, or the algorithm's task, to find out, you know, these composition property relationships. That's what Daniel is doing and these people are doing, you know, trying to extract these relationships. So glasses are fantastic materials for machine learning, and that's good for us, like for our community. Anyway, thank you very much, Daniel. We have a nice coffee break downstairs, and please, oh, today is upstairs. Today is here, just here in this salon here, up. And then please be back soon, before 10. Thank you, Daniel.
Thank you. Thank you.
Rapaz, o glass forming ability